Okay, so let's start talking about section 7.7. We're going to go ahead and skip over section 7.6 to finish off this slog of a chapter. I wanted to trim some fat somewhere because this is definitely the longest chapter that we're going to cover, and that seemed like the one place that I could do it. Towards the end of the video, I'm going to reference back to section 7.6 when I talk about a SAT algorithm, and you can go skim over that if you have more curiosity about how it works. Okay, so I'm just going to reference it but not going to go deep into it. It's basically a type of local search algorithm which you can take a look at. But anyway, so let's get into 7.7. So in 7.7, what we're going to do is kind of try to tie all these ideas that we've discussed up to this point together, and we're going to talk about agents, or how you can build an agent that uses this propositional logic, right? So we've talked about doing some proving, we've talked about putting together a knowledge base, we've talked about entailment, we talked about the basics of propositional logic. Okay, so let's talk about how you can build some of the principles that go into building a logic-based agent that's using propositional logic. Okay, so the agent that is going to be based off of this logic is going to need a few things, right? So we need the agent to be able to figure out the state of the world that it's operating in. Okay, so this is going to require that we have, or that we put together, a complete logic model that is going to detail the effects that the agent's actions can have on the world. Okay, we're going to need to know or show, or you're going to have to be able to have the agent be able to keep track of the world in an efficient way, right? We don't want the agent to have to go back through the entire percept history. We want it to be able to, within a limited scope, or within a particular scope, have the agent be able to make inferences and make decisions. Okay, and then we're going to need that agent, with all of this information, we're going to need it to be able to make plans. And by that we mean, well, here's the series of actions that I'm going to take to solve whatever the problem may be. Okay, so what about the current state of the world? So we know that we've got this knowledge base, and we started putting it together earlier on, right? We started going through and using all of these axioms and percept sentences from the agent's experiences, so that the agent would have some knowledge that it could use to deduce what it should be able to do, right? So we had axioms such as what the starting square was, right? P11 starting square, there's no, or excuse me, square 11 is the starting square and there's no pits there. Okay, and we also knew there was no wumpus. So we could have an axiom sentence, not W11, not P11. Okay, and so we went through and we put together a large collection of sentences as we discussed propositional logic. We discussed the knowledge base. Okay, so here some more examples, right? So starting square has no pit, not P11, no wumpus, not W11. Specified here with this sentence, that it's going to be breezy, that square 11's breezy, if and only if there's a pit in 1-2 or 2-1. Similarly, if there's a stench in 1-1, then there's going to be a wumpus in 1-2 or 2-1, right? And so we can go on and make a large collection of this, right? You need to have a whole bunch of sentences, repeated, that are similar but just slightly different. So, for example, breezy if neighbor has a pit, just having B11 if and only if P12 and P21 wouldn't be enough. You'd also have to have an if only if statement for B12, B13, B14, B21, etc., right? So the knowledge base would get pretty darn big. Okay, so the agent knows that there's going to be exactly one wumpus, and so you'd have to state this in a couple of ways, right? There'd be two different pieces to that. You'd have to say, well, there's a wumpus in 1-1, or there's a wumpus in 1-2, or there's a wumpus in everything in between. There's a wumpus 4-3, there's a wumpus at 4-4. So you could say there's a wumpus at any one of these places at 1-1, or 1-2, or 4-3, or 4-4, or one of the squares in between. But you'd also have to say that there could be at most one. Okay, so for all pairs of squares, we'd have to be adding, all of these sentences too, right? There's no wumpus at 1-1 or no wumpus at 1-2. There's no wumpus at 1-1 or no wumpus at 1-3, right? So that would go through all the possible pairs of squares that you could have. Okay, now what about different percepts that an agent could experience? Okay, now there's a slight problem here, because if an agent moves into a square and detects a stench, okay, if it detects a stench, okay, you add that to your knowledge base, right? So that gets tacked on to the set of all sentences, right? But then if you move into another square and that square has no stench, well, then you add on no stench to your knowledge base, right? So at that point, you kind of have a problem, because you've got two sentences that cancel each other out. So we need some kind of a cure to that. We need some way to be able to address that. And the way you can address that is by introducing this concept of time, right? So for example, if the agent on turn 3 moves into a square and detects that there's no stench in that square, okay, so then you can add to the knowledge base no stench, but tack on some kind of delimiter, some kind of notation that says, well, on turn 3, no stench, right? So when I took my move on turn 3, when the agent moved, when I moved the player around in the wumpus maze, no stench on turn 3, right? Then on turn 4, if you make another move, say you go north, you go east, or whatever, and then you get a percept for a stench, well, now you add stench on turn 4, right? So these are actually different literals now, and they're not going to cancel each other out. Okay, so this idea of time and its relationship to percepts, okay, or to other parts of the knowledge base, can work for any part of the world that can change, right? So the location of the agent, right? So that can change, right? So on time 0, when the game first starts, the agent is in 1-1, square 1-1, right? But if the agent moves north 1, well, that's a second later, and so you'd add an additional entry to the knowledge base, L1 with sub 1-2, right? So you can add this idea of time, and it'll apply to anything that can change, right? So any part of the world that changes, right? There's a term for that, and that term is fluent. Okay, so part of the world that you're working with that can change is called a fluent. Okay, now when you have permanent aspects of your world, for example, the wumpus is never moving. Okay, it's not mobile. It's going to be fixed. Okay, so when you have something like that, then you've got a part of your world that doesn't need a timestamp. Okay, and those things are called atemporal variables. Okay, so we can go ahead and connect percepts of stench or breeze directly with the squares where they're experienced through using the location fluent, right? So this is what it can look like. So this is called, or the textbook verse to this is asserting the location fluent, right? So if you have a certain time step t, right, maybe turn 1, turn 2, turn 3, and some particular square x and y, then you can say that your location at a given time in a particular square is going to imply that there's a breeze at that time, right? A breeze at that time, if and only if there's a breeze in that particular square. That's what that means, right? So similarly for the stench, if at a particular time the location of the agent is in square xy, that's going to imply that if there's a stench at that time, or it will imply that if there's a stench at that time, if and only if there's a stench in that particular square. We're going to need next, now that we have this type of language, we're going to need to put together a set of sentences that's going to enact our transition model. Okay, so that transition model we'll use to keep track of all the fluents that we're gonna need to produce to set this up. Now to do that, we're gonna need to come up with some symbols for representing actions, right? So we're gonna need these symbols for the different actions, and we'll attach time to them. Okay, so if you got forward 0, right? Forward 0. And what that would mean is that the agent's going to move forward at time 0. Okay, so with this particular notation, you can write it a couple different ways, but the way we'll write it is that we'll have the percept for the time going first, and then the action. Okay, and then the action. So to describe how the world's going to change as part of this transition, what we'll do is we'll write these things called effect axioms. Okay, and so what they do is they're going to go ahead and say, well, this is going to be the result of the action, right, in the next time slice or in the next increment of time. Okay, so we want to say, well, if you take this action, then this is going to be the result that takes place in the next second or the next turn or whatever the unit of time that you're using. So for example, we've got an agent that's in square 1, 1 facing east at time 0. Now if the agent goes forward, which would have it transition into square 2, 1, then if we want to make notation for that, here's a sentence in the logic that can do that. So let's look at this first literal here. So we've got, location time 0 of the agent, square 1, 1, and it's facing east at time 0, and decides to move forward at time 0. Well, that's going to imply that the agent, right, it's going to imply this conjunction right here, that the agent at second 1 is in square 2, 1 and not in square 1, 1 at that particular instance of time in the next second, in the next turn, right? That's going to be the result of that action, facing east, moving forward at square 1, 1 at time 0, right? Once that's complete, you're in time segment 1, agent's now 2, 1 and not in 1, 1 anymore. Okay, so the knowledge base is going to grow quite a bit because that's going to require a sentence be constructed for each time step, for each of the 16 squares, and for each direction, right? So this is growing pretty fast. And then that's just for the one action, which was to move forward. But you need to repeat that, have sentences for all, repeated over and over again for each of the other actions as well, for the grab, for the shoot, for the climb, for the turn left, for the turn right. So the knowledge base is growing pretty quick. All right, so let's move on. So let's think about what happens if the agent moves forward at time slice 0 or turn 0. Okay, that fact would have to go into the knowledge base, and that previous equation, right, this guy right here, and I say equation, but I mean this effect axiom right here, this sentence, plus all the other sentences in our knowledge base that we made that correspond to time 0 would allow the agent to figure out, yeah, I'm in square 2, 1, right? So remember the tell and ask stuff? Well, we can ask the knowledge base, am I in square 2, 1 at turn 1, right? And so that would evaluate the true. Yeah, fine. Okay, but if we were to ask if we still have our arrow, okay, ask the knowledge base, have arrow on turn 1, that would evaluate the false. Why? Because we forgot to include, based off of our description of the knowledge base, all the stuff that remained unchanged. Okay, so this situation, this problem, has a name, and that's the frame problem. So how can we resolve this frame problem, right? So one way to do it is to have these things called frame axioms. And what you're doing here is you're writing sentences that are spelling it out, that's what propositions are unchanged, right? So example, for each time t. Okay, what this says is that if you move forward at a certain time, you have an implication that you'll have the arrow at time t plus 1 if and only if you had the arrow at time t, right? Similarly for the wumpus, right? This is spelling it out that if you move forward at time t, that the wumpus is going to be alive at time t plus 1 if and only if the wumpus was alive at time t. So, there's a whole bunch of these sentences that you'd have to add to your knowledge base, and this can be, really inefficient, right? And so this specific problem where you have to lay everything out is often called the representational frame problem. So how to resolve the representational frame problem? A solution: make your axioms about the fluents, not about actions. Okay, so what you do is you have these axioms that are defining truth for fluents that are coming a turn later, a second later, a time slice later, and then you specify the actions that could happen a second later, right? So here's how the form that it can take, and this is referred to as the successor state axiom, right? Where the fluent a second later is going to be the fluent a second later if and only if there's some action that causes it from the previous second, right, or from the previous time slice, okay, or there is the previous fluent, the fluent from the previous time slice, and there's not an action that's causing it to not exist. Sounds really abstract, sounds really crazy, but we'll look at a simple example here, right? So what this says is, what the sentence is telling us is, a second from now, or a turn from now, t plus 1, you'll have an arrow. That'll be true if and only if you had the arrow a second before, or a turn before, and you didn't shoot it that turn before, right? So have an arrow at time t and you didn't shoot at time t, then that means that you're going to have an arrow at time t plus 1. Now location, a little bit more involved, right? So what this sentence is saying is that at time t plus 1 you'll end up in square 1 1 if and only if at time t you were in square 1 1 and you didn't move forward during time t, or there was a bump a second from now, right? So this is saying, hey, if you didn't move forward or you bumped into a wall and you were in square 1 1, well, the result of that's going to be that you're in square 1 1, one turn in the future. Or if you were facing south at turn t and you moved forward at turn t, then if both of those things were true and you were at turn t in square 1 2, then you're going to end up in square 1 1 one turn from now, t plus 1. Or a way that you could get into square 1 1 a turn from now is if you were in 2 1 and you were facing west and you moved forward the turn previously, right? So you can look at it both ways. This is though here going to be the result of any one of these actions. The L11 with the t plus 1 up here, that's the result of any of the actions from one turn prior. Either this action here, or this action here, or this action here. Alright, so if we have defined these successor state axioms, and you have all the other axioms that we've talked about up to this point defined in your knowledge base, then the agent is able to ask anything that could be possibly answered, or that could have an answer in the world in which it's operating. So let's say that you had the initial sequence of percepts and actions taken by the agent, right? So you start on turn 0 and the agent detects no stench, no breeze, no glitter, no bump, no scream. and as a result moves forward, right? And then on the next turn detects no stench, no breeze, no glitter, no stench, no breeze, no glitter, no bump, no scream, and so then on that turn decides I'm going to turn right. Next turn, turn 2, second 2, time slice 2, whatever, no stench, detected a breeze, detects no glitter, no bump, no scream, and decides to turn right on that turn, and so forth, right? Given all of those percepts and all of those actions at that point in time, after turn 6, or on turn 6, I should say, right, it can determine where is it? Where is the agent located? Given all the information that's in our knowledge base, you can ask the knowledge base, on turn 6, am I in location 1, 2? And that would evaluate the true, and the agent would be able to deduce where it's at, where it's located within the Wumpus world. Even further, you could ask the knowledge base, well, where's the Wumpus, right? If you ask the knowledge base, hey, is there a Wumpus in 1, 3, and that evaluates the true? And if you ask the knowledge base, is there a pit in 3, 1, and that evaluates the true? Then the agent found the Wumpus, and the agent also found a pit, right? So, by building up this knowledge base, we're building up the ability to query the knowledge base about certain realities in the world, and then based off of those realities, the agent can ask questions about, well, what should I do next? So for example, can I move to a square? Okay, well, we can add an axiom for that. So let's use propositional symbol OK, right? At time t, is it okay for me to move into square x, y? Well, that's going to be true that it's okay to do that if and only if there's no pit in square x, y, and it's not the case that there's a Wumpus in x, y, and that the Wumpus is alive at that time, right? So then you can ask the knowledge base, hey, is it okay on turn 6 to move into square 2, 2, right? If that evaluates to true, well, go ahead, move to square 2, 2. So the basics of the logic are there to get something working, right? But there are unusual exceptions that maybe you could add to the rules of the game, right? What if the agent trips? What if the agent has a heart attack? What if the agent gets eaten by a bat? What if a dragon shows up, right? So, you have all these different possibilities that you could add to your game or to your environment that could impact how big the knowledge base is going to get for having to deal with all these different conditions, right? So being able to specify all of these conditions, all of these exceptions, there's a name for that. It's called the qualification problem. And the more of these exceptions you throw in to the possible movements that an agent could take, the slower things get, the less efficient things get, right? So there's no best overall solution, right? What's the best way of dealing with it? Depends, just like anything else. Now, chapter 13 goes into probability theory, which can help, which if we have time left in the semester, we're going to get to. But this is a problem that developers of intelligent logic-based agent or rational logic-based agents have to deal with, right? It's always this trade-off of resources versus what you're trying to do. Building a hybrid agent tries to combine the best of the search algorithms from chapter 4 and chapter 3 with these rules, these condition action rules, this knowledge base, this idea of logic, to get the best overall performance. Okay, so figure 7.20, which we'll take a look at here in a second, has pseudocode that lays out how such an agent could work. Okay, so here are the big elements of it, the highlights. So the agent is going to need to keep an updated knowledge base and an updated plan with what it needs to do, or what it's going to do, okay, or what it wants to do, what's its next move, for example. Okay, the knowledge base needs to be initialized with those atemporal axioms, those axioms that aren't going to change with time. For example, no pit in square 1, 1. That's not going to change. Now, as time goes on, as turns are taken, as seconds pass, however you want to quantify the passage of time, percept axioms are being added, as well as all of the axioms that are related to time as it changes, right? So, those successor state axioms. Then the agent uses asks to determine which moves it should make, which are the safe moves, to infer what are the safe moves. Okay, so here's the pseudocode for it, and I'm not going to go through the entire thing in the interest of time. You know the drill at this point. I'll just point out a couple of things here to get you started. So, what's the input for this thing? A percept and an action that the agent should take within the game. So you've got percept, which is a list. Remember, it was going to be, was there a stench, was there a breeze, glitter, bump, scream. Remember, we were building a percept list. What's persistent? The knowledge base. It's got the atemporal Wumpus physics in there. You got a time counter, 0, and you got plan, which is an action sequence, which is initially empty, right? So that stuff's around in between calls to this function, right? So remember when we were talking about, what's the first thing that happens? Tell the knowledge base about your percept sequence at a particular time, okay? And then what you do then, when you take a look at all these different ifs here, is it's going through and it's saying, all right, well, I'll go ahead and start off by looking at the stuff that's most important, okay, and ask some specific questions about what I should do, right? Make a priority list, okay? So that's what this first guy right here at the very beginning is doing, right? And you're specifically asking, well, hey, knowledge base, did I just detect glitter at this particular time? If I did, then I'm going to do the action grab plus call this plan route function, which is going to try to determine, what's the safest escape route for me, right? I'm in the current location. I want to get to square 1, 1. I want to make sure that it's safe to go to, and I want to climb once I get there, right? So you're planning out this route, okay? And so you have extra if statements here that just go through and prioritize the actions you want to take in a particular order, because they're evaluated at the very, 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 very beginning, okay? Or sorry, I say at the very beginning, but I mean in order of their importance, okay? Right, so the plan route function takes current, goals, allowed, returns an action sequence. This is the sequence of actions you should take: forward, turn left, turn right, shoot, etc. The inputs, current, the agent's current position, goals, set of squares. We want to get to one of those squares, right? You saw when I was going through that first if, there's 1, 1, that's where we want to go to. And then allowed, a set of squares that can form part of the route, any square that's safe, okay? And so what happens is that this thing uses the A* graph search to plan the route, to build the route, okay? So there's all those different elements to it, and again, I'll let you on your own go through all the different pieces, but I just wanted to highlight a few things just to kind of get you oriented, okay? So the main body does what? Makes a priority plan. First thing it wants to do is try to make a plan to grab gold and leave. The second is make a plan to travel to a safe square, using A* search. If there's no safe square, make one by shooting an arrow, right? And then see if there's a Wumpus there. If not, plan to make a shot. Find a square we don't know for certain is unsafe, okay? And then the last thing is, if there's no safe way to get out or to get the gold, whatever, go ahead and leave. So this is the main body of the function. That's what these series of ifs are doing. So again, read through that, understand what's happening at a high level, try to dissect it piece by piece so you can understand. You should be able to read the pseudocode by now, okay? Okay, so what we've put together so far works, right? But the longer the program would run, the slower it's going to become, right? It's going to become less and less efficient because as the agent is wandering around making decisions, perceiving its world, its knowledge base is growing at a linear rate. It's getting longer. Okay, you're adding sentences constantly, and so that means that the chain of inferences to determine, where am I, what move should I make, what's my plan going to be, it's just going to get bigger and bigger, take longer and longer. It's unsustainable. The longer you live, you can't be taking longer to think and decide what you should do. So what's needed to solve this problem, this should say constant time, not real time, my apologies. We need constant time updates, right? We need updates that come not in linear time, but constant time. We want to make the decision process and the updating of the knowledge base and the whole performance, right? We want to make that independent of time t, right? We don't want things slowing down as time goes on. We want it to stay at roughly the same rate of time to get stuff done. So what we can do is we can make a cache, right? So when we make an inference, we can cache that result. We can store that result, okay? So that way you're not having to repeat the same inferences over and over and over and over and over again. So you can, when time passes, you go to a next step, you can just go back to your cache and take the results of everything you've inferred up to that point and then just build on that without having to rebuild it all completely from scratch. So in what form could that take? Well, instead of tracking everything from the beginning of time, what we could do is we could replace that past history of all those percepts and all of their potential inferences with a belief state. This is going to contain the same representation of all of the possible current states of the world, but instead of using explicit states like we did before, we can use a logical sentence. Okay, so the process of updating that belief state as you're getting new percepts, there's a term for that, and that term is state estimation. Okay, so as I said just a second ago, they can use a logical sentence. The logical agents can use a logical sentence that's associated with the current time slice, the current turn, the current second, however you want to differentiate time. Okay, so this is what it could look like, right? So this is one for the belief state for second one. The Wumpus is alive, and the location of the agent at second one or turn one is it's in square 2-1. There's a breeze in 2-1, and there's a pit in 3-1 or 2-2. That's the belief state at instance 1, at time 1, at second 1, at turn 1. Okay, so translation representation of all time 1 states where the Wumpus lives, agent square is breezy, and a pit, that should say pit, is in 3-1 or 3-2 or both. So this is one representation, right, within the belief state. Okay, so now as it turns out, computationally, this is not very easy to do. If you've got influence symbols for some time or turn or slice, t, you could have 2 to the n possible states. So this is going to be, each one of those states is going to represent a combination of truth values that you're assigning to your symbols. Okay, so the set of belief states is going to be a set, it's going to be huge, because the set of belief states is going to be a set of all of the subsets of the set of physical states, right? So this could be ginormous. So if you've got 2 to the n physical states, this would mean you could have 2 raised to the 2 to the n belief states, right? So think about that for a second. Do the math on that for a second. Fill in some value for n. 10 fluent symbols, right? So you'd be doing 2 raised to the 2 raised to the 10. It's a huge number. Big idea. It's hard, right? The scale is huge. So what's a possible solution? Well, textbook doesn't go too deep into this, right? Matter of fact, it only gives you a paragraph to talk about this, but it gives you an idea, right? So you can have a approximate state estimation. You can take a guess, and what that can do, or what that can take the form of, is a representation of states as literal conjunctions, right? So these estimations are referred to as 1 minus CNF formulas, right? So how does it work in general? Well, the agent goes about trying to prove some symbol x at time t and not x time t for each symbol of xt, right? Where you have a belief state of, t minus 1, or given the belief state of t minus 1, right? So the belief state that you had a turn ago, right? The agent goes through and says, okay, well, for every single symbol at this particular time, right, I'm going to try to prove that and not that for each one of them. Okay, so the belief state of all of the provable literals, that becomes your new belief state. Okay, so you try to prove all of different literals and the negation of those literals for each one of the literals, okay, given your belief state from the previous turn. Okay, and so all the literals that are provable, that you can prove, those become your new belief state. So the old belief state, toss it. Now, as it turns out, you're going to have some data loss. Okay, so it's an approximation. And as it turns out, some of the belief states, or some states, I should say, could be excluded from your new belief state. It's a guess, and so you might not get the best guess or the actual best result, right? But what you're doing is you're just saying, let's take a guess just to speed things up. We're going to sacrifice some of our data for performance. All right, so how do you make plans using propositional inference? Okay, so the agent from figure 7.20 is going to use logical inference to find safe squares, right? So the plans are going to be made using an A-star search. And so what's the plan going to be? The series of actions to take to get the gold if it's possible and get the heck out of the Wumpus world safely, right? So how does that happen? How are those plans made using logical inference? So here's the idea. You're gonna make a sentence, right? And it's gonna have these parts. Okay, it's gonna start off with all of the initial assertions about the start state, right? So no pit in square 1 1, no stench in square, or no Wumpus in square 1 1, right? And then you have to add to that all of the successor state axioms for all of the actions, right, at each turn, right? At each turn up to each turn, each second, each time slice up to a particular turn, time t, second t, time slice t, okay? And then you have to add an assertion that, the goal, we hit it, right? We got the goal. And here's an example of that. We've got gold at time t and we climbed out, time t, that's the goal. Now you take that sentence and you give it to a SAT solver. Okay, now the SAT solver is that thing that I talked about from the previous section, 7.6, which I said I was going to skip over really quickly. Basically what that thing does, if that solver can find a model, right, a model that satisfies this sentence, then you can achieve your goal, right? If the sentence can't be satisfied, then what that means is that this problem, it's impossible. You're not going to be able to get the gold and get out, right? The planning problem is impossible. Now, if a model is found, what you do is you take from the model the variables for all of the actions that are representing those actions and that have true assigned to them. Okay, now all of those variables, they represent actions, they're true, all of those actions, that's your plan. That's your plan. All of the variables that represent an action that are assigned true, take those together, they form the set that makes your plan. All right, so let's look at the pseudocode algorithm for this that's encapsulating all of these ideas, right? An example solver, right? So what this does is this is going to give you your plan, a solution, right? Or failure. So what are the inputs here? Well, those initial sentences, all of your transition sentences, your goal sentence, and that all those inputs, that's going to be description of the problem. Now, we're adding something here that we hadn't mentioned so far, which is Tmax, right? So what this is doing is this is placing a limit on how long the plan can be. And remember, the plan is a set of actions, right, that you can take, that the agent can take. Okay, so by doing Tmax here, the algorithm here has, like I said, a little bit of a twist in that it's also leveraging the idea of iterative deepening, right? So what's happening is that first, you got this loop that says for t equals 0 to Tmax. So what this is doing is it's saying, well, initially let's start off thinking only about a 1-turn solution, and then a 2-turn solution, and then a 3-turn solution, and then a 4-turn solution, and then a 5-turn solution, right? Where each turn is going to be, representing an action that the agent could take. And so, this is going to keep going up until some cutoff point, right? Now, what's translate the sat do? Takes the init, the transition, the goal, a particular time, and says, all right, let's go ahead and come up with a sentence for that, representing that's in conjunctive normal form. Pass that to your sat solver. The sat solver is what I was talking about from section 7.6, and that thing's either going to return null if it doesn't find a model that satisfies the sentence, or it will return the model that satisfies it. Okay, so if the model is not null, then what? Then this function is going to return the solution. Remember what the solution was? The solution was all of those variables in the model that represent an action that's been assigned true, right? And so if it returns that, you've got your plan. The solution is the plan, right? But if not, if you go through that entire loop up to your max and it never returns a model, then you return failure. It means it's not solvable. There's no way to get out of the Wumpus world with the gold. Okay, so this is going to get you the shortest plan within your limit of steps, turns, seconds, time slices, right? Within your limit you establish for time, if there is a plan findable within that limit. Okay, so the key to making this all work is to make sure that you have a really good knowledge base. All right, phew, let's summarize. Finally done. Chapter 7, without a doubt, I think out of all of them is the longest. Probably the toughest one so far, if for no other reason that it's just a slog, and also logic, math. There's no way to get around it. If you want to understand how logic-based agents work, you have to know a little bit of logic, right? So we looked at propositional logic here. In the next chapter, chapter 8, it'll be shorter, but it's going to delve into first-order logic, okay? And that logic is going to look a lot like what Prolog looks like. And so hopefully will make your Prolog assignment and creating your expert system easier as we dig through this and get through chapter 9. So anyway, yeah, knowledge-based agents, right? So an intelligent agent needs to know about its world to be able to make good choices, be able to make rational choices. How can you encode knowledge? How do you represent knowledge? Sentences, right? And those sentences are going to be formed from a knowledge representation language. In this case, we were talking about propositional logic, okay? And those sentences are going to get stored somewhere. They're going to get stored in a knowledge base, okay? So knowledge-based agents, they need that knowledge base, and they have to have a way to make inferences to be able to figure out if your knowledge base entails some sentence. So a representation language has what? Syntax, which defines the structure of the sentence, just like any programming language. It has to have semantics, right? The meaning of sentences, and that helps to define the truth of those sentences for each possible world and the model that represents that possible world. Entailment, that's the big deal here. Sentence alpha entails sentence beta if beta is true in all worlds that alpha is true in, okay? A sentence has validity if alpha implies beta, and a sentence is unsatisfiable if alpha and not beta. Okay, so remember we gave a lot of terms at you. Okay, that's going to be kind of tough too. Inference is when you get new sentences created from old ones. Sound inferences or sound inference algorithms will derive only entailed sentences, right? Only sentences that were created from original or pre-existing sentences, and complete algorithms can derive all of the sentences that can be entailed. Propositional logic has propositional symbols and those connectives, right? So propositional symbol, P, Q, and R, logical connectives, and, or, not, implication, bidirectional, and they can handle, or it does handle, true, false, and unknown propositions. The set of possible models is finite, and you can check for entailment by using or by enumerating models, right? Remember the truth tables? Model checking inference algorithms include backtracking and local search methods, right? Now we didn't dig into the local search, methods or backtracking, right? That was also in chapter or section 7.6, but it's in the summary, so I'll mention it if you want to know more about backtracking and the local search methods. 7.6. Inference rules provide for sound inference used to find proofs, right? And the resolution rule gives us a complete inference algorithm for knowledge bases, okay? And what we need is the conjunctive normal form to express that. We talked about forward chaining and backward chaining, and these set up very natural, very human followable, human understandable algorithms for knowledge bases that are limited to sentences that are in horn form, right, using horn clauses. Okay. All right, so local search methods, again, we skipped over that. That was section 7.6. Logical state estimation, that's going to give you a logical sentence describing all the possible states for a history of observations, right? So update, right? To update that stuff, we're going to need inference to update our state. We're going to have a transition model, and it's going to be built using successor state axioms, which we talked about, and they specify how the fluents change. Now, propositional logic, as it turns out, doesn't scale well, right? In situations where you have environments that are not bounded by their size, and they have problems, as it turns out. We didn't dig into this, right? But they have problems when expressing time, space. They can't really do it concisely, right? Patterns of relationships between objects. It's for that knowledge base. I talked about how we had to list all these different sentences, right? We had to say, well, there's a wumpus somewhere in the world, so you could make a disjunction. Wumpus in 1.1, or wumpus in 1.2, or wumpus in 1.3, or wumpus in 1.4, or wumpus in 2.1, or wumpus in 2.2, right? And then you'd have to have a whole bunch of sentences, not wumpus 1.1, or not wumpus 1.2, to try to express the fact that you can't have more than one wumpus, right? And having to specify, if there's a breeze in 1.2, if and only if a pit in 2.1, or so you have a ton of these sentences that make up your knowledge base. So you can't really concisely, it can get really difficult capturing all of those sentences, right? And so first order logic tries to deal with that, and that's what chapter 8 is going to be about. Whew, finished.